In this video, Newton's second law will be used to analyze a real-life model of a moving object that moves in one steady direction with constant velocity. The model I made was one of a rolling tennis ball. Using Tracker to observe and explore the model, I placed a coordinate axis onto the screen. The coordinate axis is adjusted to fit the slightly unlevel camera angle. The origin of the axis is in the center of the ball. As you can see, the ball is being rolled in the positive x direction. I tracked the center of the ball while the video progressed and produced a list of calculations from the Tracker table, but we will get to that soon. The graph made for the model has a vertical line that accounts for the x plots, and a horizontal line that accounts for the time elapsed. This model produced a fairly straight linear line that slopes in an upward fashion. Going back to the data collected from Tracker, we see that the starting time is 0 seconds, and the ball's initial position is negative 0.003 on the x-axis, and negative 0.002 on the y-axis. Furthermore, the velocity is calculated by the change in rate by the change in time. So, plugging in this data, we will get that the velocity is equal to negative 0.63 meters per second. It is also good to point out that the time of the last observation is 2.167 seconds. So, if we plug in all this data into specific spots in the v-idle, like this, pause, then we will get our desired computer model, which is a perfect linear line that slopes upward in the positive x direction. The ball here is moving in the same direction as in the experiment. But as we saw in the Tracker earlier, the ball does not run in a perfectly straight line, but rather drifts a bit from the start. That is why when I compared the computer model with the experimental model in Google Spreadsheet, the lines are not completely alike, although the general direction is somewhat accurate. Let's take a look at Newton's second law. Newton's second law can be rearranged to show that acceleration is equal to net force divided by mass. Furthermore, acceleration is equal to the change in velocity divided by the change in time, change being denoted by the delta symbol. This can be simplified to the equation which is used in the v-idle code here. In the experiment, we are going to assume that there are no other surrounding forces other than gravity, and therefore net force is equal to 0, and the mass and time elapsed is inconsequential. If I were to change the orientation of the axis to make the left side positive x and the right side negative x, as well as the bottom side positive y and the top side negative y, then the graph of the model would change from being an upward slope to being a downward slope. Finally, the assignment asks if it is possible for me to say how many pushes and pulls are added together to give a zero net force. My answer is no. Newton's second law simply states that F net is a single entity that is a sum of the net forces, and this makes it impossible to see every single push and pull, as well as see how many there are.